Alrighty, good morning, guys. Welcome back. Today we are going to pick up where we left off last time, talking about graphs of parametric equations and how to do calculus operations with them. I'm teaching my pre-calculus students about matrices. So time is limited. I appreciate you guys coming here. I know the Wednesday before Thanksgiving is one of those days where it can be tempting to not show up. Appreciate the discipline you're displaying here. Zaid, I'm glad to see you here. I've been wrestling with the people in G25, specifically about your paperwork. And I did finally get word back from them that they found it. The people at the testing center, some of you found emails from me, lost some shit. And it's been deeply frustrating. So I went by there like 3 times, bugging them. Hey, can you look for this? Hey, can you look for this? Hey, can you look for this? And every time they look and they say, no, we don't have it. No, we don't have it. No, we don't have it. So I finally got annoyed and emailed the administrator in charge over there. And she miraculously found the shit. So fucking, I don't know what's going on over there. But I just wanted to let you know. So today, let's have a card going here. This is MAC2312 section 004. Date is the 24th. About to finish talking about calculus with parametric curves. Section 10. So if there's time, we might introduce polar coordinates. We're getting there. Prashant, let me see. So I got a stack from these people the other day. So from the random weird stack that they lost, Kylie's, Juan's, and Enrique's have been graded. And from the random weird stack that they lost, the stuff that I haven't gotten to yet, let's see, this is David, Zaid, Jose, Tiffin, Prashant, yeah, you're in here, Kin, and Miguel. So mystery papers have shown back up, and we're getting to them as quickly as I can. All right. So calculus with parametric curves. We talked about tangent line stuff, first derivative stuff. We can ask you to construct the tangent line to a parametric curve. We can ask you to determine the points where a parametric curve has horizontal or vertical tangents. We talked about how to find the area bounded by a parametric curve and the x-axis, although that was kind of boring because it turns out to be the same shit. You can only do it in the situations where the thing behaves like a regular function, and in that case, you get the same result. I also gave you the formula for the arc length of a parametric curve, and we discussed just a tiny bit where that comes from. I want to show you that in some detail here today and do some calculations for you, because those arc length integrals, those are cool. So the arc length of a curve is the length you would find if you straighten and measure the curve. All right, so if I have some plane curve, like this, and I were to take that thing, call this P0 and call it Pn. If I were to take that curve and straighten it out and put it on a ruler, how long would it be? What's that length? And since it is the length of an arc, right, a curve, we call it arc length. The actual geometry of taking a curve and straightening it out is quite complicated. So rather than doing precisely that, what we do is we chop the plane curve up into a bunch of short segments, each one we approximate the length of by a straight line. So the theorem I already gave you. The formula. The arc length of the parametric curve x equals x of t, y equals y of t, where t runs from A to B, is given by, we require that the x and y functions both be differentiable. The symbol your book uses is L. It's the integral from t equals A to t equals B of the square root of dx dt squared plus dy dt squared all done dt. And depending on what dx dt and dy dt are, this square root can be a bitch and a half to integrate. Because we've got this addition going on inside here. We know we can't split that up. That's not dx dt plus dy dt. Square roots do not play nice with addition or subtraction. And if this looks kind of like a Pythagorean thing to you, that's because it is. It's very much like the Pythagorean theorem. Quick proof. What we do is we chop the time interval AB into n equal length subintervals. So kind of here's your time interval. B, and I've chopped this up into a bunch of little pieces. Each one having width delta t. So A I call T0, then this would be like T1, T2, T3, I'll call this Ti minus 1, call this Ti, and B we call Tn. And each one of these little time intervals has width delta t. Delta t would be b minus a n. And what this does to our curve, this segments our curve into pieces, which we can approximate as straight lines. So over here, I'll draw my curve. Here's my initial point. With something like this. Here's my terminal point. So this point I'll call P0 is the point associated with T0, or A, the time T equals A, it's my initial point. P1 maybe. P2. P3. Maybe here I've got Pi minus 1. Here I've got Pi. I'm going to come over here to Pn. All right, the second to last point here would be Pn minus 1. So here's my parametric curve. This is the x-axis. This is the y-axis. And each one of these t values corresponds to a point on the curve. Now, the exact length from P0 to P1 would be the length of this little black curve. I don't know how to find that, but I can pretend like that curve is a straight line from there to there. If I have enough of these P's, then that will be a pretty accurate approximation. I've got a bunch more P's in here. So I'm not going to draw the ones between the dot dots. Here I have this one. And the last one would be like this. All right, so I chop up my curve into a bunch of little curve pieces, and then each one of those little curve pieces I pretend is a straight line, which is not true, but it's a reasonable approximation. Okay, and in between the dot dots, there's more things, right? Like in here is P4, P5. I'm just using this as like a generic Pi minus 1 to Pi. And there's more of them in here, and then last one like this. I'm going to keep this picture visible and start trying to write down a formula for the arc length, or at least the approximate arc length. Let this denote the length, the straight line length from P0 to P1. P1, P2 be the length from P1 to P2 in general, and Pi minus 1 to Pi be the length from Pi minus 1 to Pi. All right, the blue lengths. And L is approximately the length from P0 to P1 plus the length from P1 to P2 plus all the way out length from Pn minus 1 to Pn. L is the exact arc length. And each of these is the little blue distance. This can be written as sigma I from 1 to n, length Pi minus 1 to Pi. Right, you plug in I equals 1 here, you get P0 to P1. Plug in I equals 2 here, you get P1 to P2. So if I can find a formula for the hypotenuse of this little right triangle in here, the length from Pi minus 1 to Pi, I'll have a nice formula for this sum. Let me call this distance here delta yi, I'm sorry, delta xi, and call this distance here delta yi. It's the little change in x from I minus 1 to I, that's this, and the little change in y from I minus 1 to I. And by the Pythagorean formula, damn, I can't. By Pythagorean theorem, the length pi minus 1 to pi squared is delta xi squared plus delta yi squared. Right? A squared plus b squared equals c squared. Which means that the straight line length from pi minus 1 to pi is the square root of delta xi squared plus delta yi squared. Plugging this in to the approximation below, I get sigma I from 1 to n square root of delta xi squared plus delta yi squared. And the sneaky move here is to multiply by delta t over delta t. I'll do it in a separate one. We get sigma I from 1 to n square root delta xi squared plus delta yi squared times delta t over delta t. And I can shove that delta t from the downstairs into the square root as 1 over delta t squared, leaving the delta t from upstairs outside the square root. Then distributing, we get sigma I from 1 to n square root of delta xi squared over delta t squared, which is delta xi over delta t all squared, plus delta yi over delta t all squared, with a delta t outside. As n goes to infinity, several things happen. Period. As n goes to infinity, this formula becomes exact. Because I'm using infinitely many points, right? This curve is made up of infinitely many points. And as n goes to infinity, these blue segments each get smaller and smaller and smaller, and we get closer and closer and closer to the actual arc length. And delta x over delta t, right? Delta xi over delta t, if you like. You know what deltas do as you go to infinity here. These are going to become derivatives. This becomes dx dt, and delta yi over delta t becomes dy dt. And finally, the sum above, which is a Riemann sum, becomes an integral. Namely, well, so L is equal to integral of the square root of, this becomes dx dt squared, plus this becomes dy dt squared, delta t becomes dt, and the Riemann sum is for the integral from a to b, from t equals a to t equals b, right? That was my time interval that I chopped up at the start. And that's the proof. Details of the proof not super important, but I do want you to recognize that this thing right here represents a little element of arc length. We call it ds. It's a little differential element of arc length. Yes, the classical symbol for arc length is a lowercase s. Your textbook, for reasons I don't understand, chooses to use the symbol L for arc length. I think it's a bad choice, but I can't tell them not to. So integral, they use alpha and beta, right? Same picture. You take your curve. Oh, look, their curve, it looks like mine. Take your curve, chop it up into straight line pieces. Each one of those straight line pieces you can calculate the length of, and we get the integral that we wanted. So yeah, we call this thing ds. Thing inside the integral here, we call ds. And we can use this formula to find the length of a bunch of different curves. Let's do, fuck it, let's do the unit circle. The things you need to remember here, really all just right here. This is the formula for arc length. And a single, like the thing you're integrating here, the little tiny differential bit of arc length we call ds. Just like the little volumes we called dv. So let's find the length of the curve. X of t equals cos t, y of t equals sine t, where t runs from 0 to 2 pi. That we know is the unit circle, right? That is the standard parametrization of the unit circle. So this example before. Starting here, walking around, and ending back there. The way I encourage you to do this is to write down ds, because usually you're going to want to do some simplification. In fact, you might want to write ds squared. This is dx dt squared plus dy dt squared. And dx dt, the derivative of your cosine function. It's negative sine t. Dy dt is the derivative of your sine function, which is cos t. So ds squared is negative sine t squared plus cos t squared, which is sine squared t plus cos squared t, which is 1. So ds is the square root of 1. Therefore, the arc length, I guess 1 dt, I should say. So the arc length here is the integral from 0 to 2 pi of ds, which is the integral from 0 to 2 pi of the square root of 1 dt. Square root of 1 is just 1, so this is just the integral from 0 to 2 pi of dt. This is like a zero work problem. Integral of dt is just t. And we evaluate from 0 to 2 pi. So that's 2 pi minus 0, or 2 pi. And hopefully we all knew that, right? Hopefully we all knew that the circumference of the unit circle is 2 pi. But, you know, it's nice to verify that this formula works. If you don't like writing out the ds separately, you can just write down the formula for the arc length, right? You can just write down the integral at the start, but crunching out ds has its advantages. We'll see that later when we talk about surface areas. Cycloid, not a big fan. We haven't derived the cycloid thing, and then they jump straight to surface area. So let me grab a problem from later here. Find the exact length of the curve. Okay. You'll see is that some of these arc length integrals tend to be quite challenging. Let me do 42. Find the length. I'm going to write this down, then I'll switch back. X of t equals e to the t minus t. Y of t equals 4e to the t over 2, where 0 is less than or equal to t is less than or equal to 2. So what do we need? We need dx dt, the derivative of the x function. That's e to the t minus 1. And dy dt, which is the derivative of the y function. This requires the chain rule. That's 4 times e to the t over 2 times 1/2, or 2e to the t over 2. And then your integral, I'll just write it out this time instead of writing out ds. That is the integral from 0 to 2 of the square root of dx dt squared plus dy dt squared dt. which is the integral from 0 to 2 of the square root of this thing squared. So that's e to the t minus 1 squared plus this thing squared to e to the t over 2 all squared dt. And at a glance, this integral is quite intimidating. Remember, these squares and this square, they don't cancel because of this addition going on in here. We cannot give the square root to each of these pieces separately. That doesn't work. So the only thing to do is to like multiply these out and hope that something nice happens. Hope that we get an integral that we can manage. And oftentimes we cannot. It's hard to come up with good arc length problems. If I square out e to the t minus 1, that's e to the t squared, or e to the 2t, minus 2e to the t plus 1 FOILing. If I square 2e to the t over 2, I get 4e to the 2 times t over 2 is e to the t. And you notice that this term and this term are like terms. This is integral 0 to 2 square root of e to the 2t, negative 2e to the t plus 4e to the t is plus 2e to the t plus 1 dt. And then e to the 2t plus e to the t plus 1 factors. This is one of those factoring tricks that we learn in pre-calculus. This is e to the t plus 1 all squared dt. There. So that e to the 2t plus 2 e to the t plus 1 is e to the t squared plus 2 e to the t plus 1 is the same as e to the t plus 1 times e to the t plus 1. You factor it like a quadratic. And that's e to the t plus 1 all squared. So that's kind of the magic step here. Because once I'm able to factor this as a perfect square, now I've got the square root of some chunk, and that whole chunk is squared. Now the square and the square root do cancel. And I get the integral from 0 to 2 of e to the t plus 1 dt. So the antiderivative there, e to the t plus t. I evaluate that from 0 to 2. And that gives me a squared plus 2 minus e to the 0 plus 0, which is e squared plus 2 minus 1, or e squared plus 1. This is a fairly typical arc length problem, right? This is about par for the course. Okay. Maybe even on the easier side, as far as arc length problems that we can actually solve go. Remember what I said a second ago, most of the arc length integrals that you write down, if you just take any one of the random parametric curves from the previous homework set and you try to write down the arc length integral for it, you will find that most of those integrals are extremely hard. And I know you don't want to hear this, but this is where power series come back into the picture. I'm not going to do it to you. Okay. I'm not going to make you set up an arc length integral as a power series because I think that would be a little bit cruel. But remember, one of the big reasons we learned power series is so that you can evaluate integrals of functions that otherwise we couldn't integrate because they're too hard. So you write the function as a power series, integrate the power series instead. This is one of the big applications of power series. Certainly not the only one, but it's one of them. And there is a problem in your textbook about finding the arc length of an ellipse, which turns out to be a real big challenge. Arc length of a circle, the thing we just did, easy peasy. But if you replace that cos t by 2 cos t, that circle gets stretched out into an ellipse, and now all of a sudden your Pythagorean identity that made that so nice, the sine squared plus cos squared equals 1, doesn't apply. Sine squared plus 4 cos squared, that's not equal to 1. It's not equal to any constant. It's in fact quite complicated. So I just want to warn you that arc length integrals tend to be kind of a pain in the ass. They tend to be really difficult. Let's do one more. .45 is a lot of fun. Maybe something that's not quite so spoily. 43. Yeah, I like 43. And first, let me show you the picture here. So we know that cos t comma sine t on its own, that's the unit circle, right? X of t is cos t, y of t is sine t. I change that to t cos t comma, well, let me do this in steps. So I change that to 2 cos t comma 2 sine t. That stretches out the radius to 2. If I made this 3 cos t comma 3 sine t, that stretches out the radius to 3. If I make this t cos t comma t sine t, where the kind of radius is now the variable t, that means you've got something that's trying to be a circle, but the radius is always growing. It's a spiral. It's a special kind of spiral called an Archimedean spiral, where the radius is growing at like speed 1. Every time you go around 1, your radius goes out 1. You go around 2 pi, your radius goes out 2 pi. So spirals like these, there's lots of them. You put any kind of monotone function here. Let me see if I can do this. Yeah, it'll play with me. So I need to make this from 1 to somewhere. Yeah. It's like 6 pi. So if your radius is like the natural log of t, then you'll be growing in a kind of fast at first and slowing down because the natural log function grows fast at first and then slows down. If I make this a fast growing function like e to the t, your radius will grow really, e squared, no, e to the t, then your radius will grow really, really quickly because e to the t grows really, really quickly. If I make this something like t squared, then your radius will grow as a quadratic and your spiral will grow faster than the Archimedean spiral, but much slower than e to the t. So what we want to do is find the exact length of the curve t sine t comma t cos t from t equals 0 to 1. That's the length of that Archimedean spiral. But not much of it, just from 0 to 1, so not a full revolution. All right, so we're going to find the length of the curve x equals t sine t, y equals t cos t, where t runs from 0 to 1. Same stuff, just kind of plug and chug. We're going to use that arc length formula. This time I will write out ds. So ds squared is, I'll just write it as, it's kind of unpleasant to write this way. So yeah, ds is the square root of dx dt squared plus dy dt squared dt. dx dt and dy dt each require a product rule. So dx dt, if I differentiate t sine t, that's 1 sine t plus t cos t dy dt, same thing, needs a little product rule. That's going to be 1 cos t plus t times negative sine t, or minus t sine t. So if I want to plug this stuff in here, I'll get the square root of sine t plus t cos t all squared plus cos t minus t sine t all squared, and all of that is under this big square root dt. And we can try to clean this up. If I FOIL this first piece out, I get sine squared t plus 2t sine t cos t plus t squared cos squared t. That's FOILing just this piece out. Same with the second. I'll get cos squared t minus 2 sine t cos t, minus 2t sine t cos t, and then plus t squared sine squared t. All under this square root with a dt at the end. Pretty nasty. I've got plus 2t sine t cos t minus 2t sine t cos t. I've got the square root. Let's put other terms together like sine squared t and cos squared t. And then I've got t squared cos squared plus t squared sine squared. I can write that as plus t squared times sine squared t plus cos squared t factor with t squared. And then dt. Sine squared plus cos squared is 1 in each of those instances. So this is 1 plus t squared dt. So this is ds, the square root of 1 plus t squared dt, which means that the length of that curve, L, is the integral from, let's see, 0 to 1, right? Here to here, of dx, which is 1 plus t squared under that square root dt. This is a good example where you want to simplify ds before plugging into the integral, right? I don't want to have to write an integral in each of these steps. And if you wanted to omit writing the dt in the square root, that would be understandable too. You could just say dx dt squared plus dy dt squared, and then just work with these insides until you get it down to 1 plus t squared, and then say, okay, this is going to be my integral. Just because it's a lot to write. Can anybody tell me, how the fuck do I do this integral? think back to early in the semester, leading up to exam 1. This should remind you of a certain integration technique. U sub's not a bad idea. We could try subbing u equals 1 plus t squared, but I don't have a t out front here to soak up the du.
Trig sub.
Yeah, trig sub. What's the substitution? Is this a sine substitution, a tangent substitution, or a secant substitution?
Tangent.
Very good, tangent, right? It's a t squared plus a squared thing, right? So that's a tangent. You'd sub t equals the square root of this times tangent theta. Well, the square root of 1 is 1, so this is t equals tangent theta. dt then is secant squared theta d theta. You guys kind of hate me. We're going to change our bounds. When t is equal to 0, we have 0 equals tangent theta. So theta is the inverse tangent of 0, which is 0. And when t is equal to 1, theta would be the inverse tangent of 1, which is pi over 4. So this is going to become the integral from 0 to pi over 4 of the square root of 1 plus tan squared theta times dt, which is secant squared theta d theta. If you weren't angry at this problem yet, you're about to get angry at it now. So even if all this simplification didn't bother you, even if the idea of trig sub didn't bother you, the resulting trigonometric integral will make your blood boil, because 1 plus tan squared is secant squared. Square root of that is secant. So this is our old friend secant cubed. Does anybody remember how to do the secant cubed integral? This is looping integration by parts. So let me show you the expression on my face. Looping integration by parts. So we do all this bullshit, then we get to a trig sub integral, we do the trig sub, and you get a motherfucking looping IBP integral. It's the nasty case. The power of secant is odd, the power of tangent is even. Looping IBP reveals, if you forget, by the way, the IBP setup here, you choose u and dv. dv would be secant squared theta d theta. U would be secant theta. So du is secant theta tangent theta d theta, and v would be tangent theta. You would write this down and then apply a trig identity to the resulting integral, and then your integral will loop. I'm not going to go through all the details. What you get out is secant theta tangent theta plus the natural log of secant theta plus tangent theta all over 2. And this is to be evaluated between bounds 0 and pi over 4. Right, where you can say it's that thing times 1/2. So this is going to be 1/2, big curly brace. When I plug in pi over 4, the secant of pi over 4 is 2 over root 2, or just root 2. The tangent of pi over 4 is 1. Plus the natural log of the absolute value of secant of pi over 4 is root 2 plus tangent of pi over 4 is 1. Minus what you get at the lower bound, which is 1 times 0. Secant of 0 is 1, tangent of 0 is 0, plus the natural log of the absolute value of 1 plus 0. Of course, 1 times 0 is 0. The natural log of 1 is also 0. So what you get here is 1/2 times the square root of 2 plus the natural log of, this is positive, root 2 plus 1. So when I say arc length integrals tend to be a little brutal, this is what I mean. All right, we had a bunch of algebra trig simplification to do, and that left us with this, which is a trig sub thing. The trig sub's not bad, but that leaves us with this, which is pretty gnarly. It's looping IBP, which leaves us with this, which then we can evaluate between the new bounds 0 and pi over 4. So the length of this little spiral here, and we're not going out to 2 pi, we're just going out to 1. So we're looking at this tiny, tiny, tiny little fucking fraction of that thing. Oh wait, no, we just had t. This little segment of that spiral, here's more of the spiral. This little segment of that spiral has this length, 1/2 root 2 plus the natural log of root 2 plus 1. So arc length, cool, interesting, very important in a field of math called differential geometry, where you want to parametrize by arc length to kind of slow a particle down to walk along a path at speed 1. Very important in physics also, because of its importance to differential geometry. Just tends to be rough because of that formula, right? Because you've got the square root of something squared plus something else squared. Those are things that we know look like trig sub a lot, right? Often, square root of sum of squares, pretty much always a trig sub thing. A well-crafted arc length problem will allow that square to simplify quite a bit using algebra tricks like we saw in the previous example. A well-crafted but intentionally challenging arc length problem will yield a trig sub integral. And a poorly crafted or random arc length problem will yield an integral that is impossible. And that the majority of them are like that. Those are then attacked by power series. And the study of, for example, the ellipse, trying to find the length of the ellipse or circumference of the ellipse, led to the study of something called elliptic functions, which turn out to be hugely important in like many different areas of math, including the math that applies to physics, including math that applies to number theory, including math that applies to cryptography, harmonic analysis, just all over the place. But that would be beyond the scope of this class to discuss. So I'm not going to go into it. What I am going to show you in parting today, I've got a few arc length examples under our belt, is surface area. And I'm going to be gentle about surface area. but I do want you to understand the geometry, because that's the key. So this is the last bit of calculus that we will do with parametric curves. Tangents, areas bounded by curves, arc length, and surface area. Obviously, a parametric curve doesn't have a surface area. It's not a surface. It's a curve. Parametric curves have length, right? The measure of a one-dimensional thing is length. In order to talk about a surface area, I need a surface. And we get those by rotating curves. So what we're going to do here is begin with a parametric curve. Rotate about some axis and find the surface area of the generated surface. Say generated object. Right. So if I take some parametric curve, well, nice and simple here like this. X-axis, y-axis, and I rotate this bitch about the x-axis, that's going to generate, call it a manifold or a surface, a three-dimensional shape. I can do my best to try and draw that for you. This is a lot like the volumes stuff that we did at the beginning of the term. Here we would get some sort of a vase shape. Like this. All right, so this surface has a surface area, and we can compute that surface area by setting up an appropriate integral. The trick to setting up that integral is about thinking of the little arc length segment I mentioned at the end of the derivation of arc length, the ds. So if I take a tiny little element of arc length here, and I think of that as ds, that little element of arc length, when rotated, will correspond to a little band of surface area. So the big idea is that rotating a small piece of arc length ds about that same axis generates a small piece or band of surface area, which your book would call D capital S. I don't like this. Let me just leave this. Maybe DA. Let me actually see what your book uses. They use some fucked up notation here. Yeah, they do. They call it S. Assholes. All right. We won't fuck with that. Oh, all right. That's fine. So what I want to do is come up with a formula for this little bit of surface area. Maybe I'll call it dA. A for area. If I can find a formula for this, that surface area of this little blue band here, then I can integrate that to get the surface area of the whole solid, surface area of the whole manifold. And the trick here is kind of like what we did with the shells and the volume stuff. This is ds, my little piece of arc length. So if I take that band and I cut it and unroll it, then I will get something that is approximately a rectangle, where this dimension is ds, and this dimension is a circumference, right? If I think of axis of rotation poking through here. If I think of this little radius here, then this is the circumference, which is 2 pi times the radius. And in the picture here, this distance is that same radius. So if you're rotating the curve about the x-axis, then this radius would be the y value. If you're rotating about the y-axis, the radius would be an x value. If you're rotating about some other line, then you'd have to find that radius. But what this tells me is that my little surface area, the area of this band, is 2 pi r ds, where s is the, well, ds is the little arc length element. That square root of dx dt squared plus dy dt squared dt. And this is as nice as a formula for this shit gets, unfortunately. The radius could be different things depending on what you're rotating about. It could be y, it could be x, it could be x minus 2 or y plus 3. There are many ways of writing formulas like this, but this is the most general. So the sort of conclusion here is that the surface area is equal to the integral from t equals a to t equals b of 2 pi r ds, where ds is that, and r is going to be the function y of t if rotating about the x-axis, and r is going to be the function x, or x of t, if rotating about the y-axis. And this is your formula. So ds is your little arc length element, and to find the surface area, you integrate 2 pi r ds. So you gotta calculate this thing from the arc length stuff, plug that shit in there, and then if you're rotating about the x-axis, you use for your radius the function y of t. If you're rotating about the y-axis, you use for your radius the function x of t. Either way, this is going to be a dt integral at the end of the day. Your book does provide other formulas. Let me see why they do it. No, it's in here somewhere. I felt like they did. Maybe they don't. I'm not seeing it. Maybe they just do this. Boy, that's unsatisfying. Yeah, I felt like they had a spot where they kind of laid these different recipes for surface area out. Maybe that's not the case. No. All right, that's all right. That's fine then. This is what we got. So let's calculate a surface area or two. This would be the thing I recommend you save if you do flashcards. This is your surface area formula. Let's do the sphere. Let's find the surface area of the unit sphere. That is the surface area of the object generated by rotating the curve. I'll do just the upper semicircle, which is x of t equals cos t, y of t equals sine t, where, well, maybe we'll just do the lower semicircle. Why not? Keep the orientation positive from negative pi is less than or equal to t is less than or equal to 0. So this curve, this is a portion of the unit circle. It's this portion down here, traversed in this direction. And I'm going to rotate this about the x-axis. So we know, I'll just write it down, that the surface area is equal to the integral from t equals a to t equals b, 2 pi r ds. ds is the square root of dx dt squared plus dy dt squared dt, which is the square root of, well, dx dt is the derivative of cos t, that's negative sine t squared plus dy dt is the derivative of sine t, so that's cos t squared dt. And that's the square root of sine squared plus cos squared. dt, which is just the square root of 1 dt. So this is just dt itself. And because we are rotating about the x-axis, r is y of t, which is just sine t. So my surface area is the integral from negative pi to 0 of 2 pi r, which is sine t, times ds, which is just dt. And that's 2 pi times the integral from negative pi to 0 of sine t dt. Antiderivative for the sine function, negative cos t. And we'll evaluate this from negative pi up to 0. So what do we get? And this is 2 pi times the negative cos, negative cos of negative pi minus negative cos of 0. Cosine of negative pi is the same as cosine of pi is negative 1. So this is negative negative 1 is 1. Minus minus makes plus, cos of 0 is 1. So this is 2 pi times 2, or 4 pi. That's the surface area of the unit sphere. I have one more really nice example here, and it has to do with Gabriel's horn. I don't know if you remember Gabriel's horn. We talked about it when we talked about volumes a little bit, way back at the start of the term. I once put the following question on the final exam, and it was not well received. Can we, actually, no, maybe that's not smart. I don't think you guys will enjoy that. Yeah, let me take an example from the textbook. People didn't like this before, they won't like it now. It's a cool thing, but rectangle aspects of the curve. Surface area, exact area of the surface. Use a calculator node. And the exact area of the surface. Okay. Let's look at 61. X is t cubed, y of t is t squared. And we're going to rotate about the x-axis. Right. So they want us to work from 0 to 1. So we're going to take just the part here from 0 to 1, which is this guy. And we're going to rotate it about the x-axis. And that will generate a surface. T cubed and T squared, right? Yeah. So the curve here, we know the whole curve is this cusp form. We're just looking at this portion of it. From here to here and spinning that about the x-axis. So the solid we're looking at is this kind of sideways bowl-shaped thing. Something like this. And we're going to find the surface area. Find the area of the surface. We know what we need. We need dx dt, we need dy dt, we need ds. So dx dt is 3t squared. dy dt is 2t. So ds is the square root of the sum of the squares of those things. And I can try to clean this up a little bit. So what we get, this is 9t to the 4 plus 4t squared. We can factor a t squared. It'll come all the way out of the squared as a t. And what's left is 9t squared plus 4. So my surface area is going to be the integral from 0 to 1 of 2 pi times my radius. I'm rotating about the x-axis, so my radius is, I'll write it here, let's do this. And r equals y of t, which is t squared, because rotating about the x-axis. So this is 2 pi integral 0 to 1. R is y of t is t squared. ds is t times the square root of 9t squared plus 4 dt. So this is going to be 2 pi integral 0 to 1 t cubed times the square root of 9t squared plus 4 dt. And I'm going to stare at this for a minute and see if I can't come up with some way to make this less of a bitch and a half. So we look at this integral and we ask ourselves, what can we do with that? It's not immediately obvious. Anybody got an idea? Yes. Yeah. Thoughts, guesses, feelings?
Try to arrange for trig sub again.
Trig sub's an option, right? We could make a trigonometric substitution in here, something like t equals 2/3 tangent theta. The 3 squared would cancel with the 9, the 2 squared would give you a 4, you bring out the 4. But I don't think we need it. I think this one we can do with u sub. Because my differential So if I let u be the inside here, then my du is 18t dt. This t will eat up one of these t's, leaving me with a t squared, which I can replace in terms of u. Let's do the bounds. When t is 0, u is 4. When t is 1, u is 9 plus 4 is 13. So this will be 2 pi integral 4 to 13. I'll write this as t squared times the square root of u. See, one of these t's is going to get soaked up here. That makes me a t squared there. And then I'll have 1/18 du left over, right? T dt is 1/18 du. So the t I peel off here gets soaked up, or if you like, cancels. And then that t squared, I can replace by u stuff. So u minus 4 is equal to 9t squared, which means 1/9 u minus 4 is t squared. So we're going to get away with this. This is nice. I have 2 pi over 18 integral 4 to 13 1/9 u minus 4 times the square root of u du. Trig sub would work here too. It's just a pain. This is a little more slick. The 1/9 can come out. Let's see, 2 over 18, that's 9. So this is 1 over 81, or pi over 81. Integral 4 to 13. U times the square root of u is u to the 3/2 minus 4 times the square root of u is 4u to the 1/2 du. And I'm gonna run out of time here. I know we're a few minutes over. U to the 3/2 will integrate, so u to the 5/2, that'll be 2/5 u to the 5/2 minus u to the 1/2 be u to the 3, integrate to u to the 3/2, so it'll be 2/3. This is the 4 there is going to be 8/3 u to the 3/2. And we'd have to evaluate this between 4 and 13. I'm going to stop here because I do have another class that begins at 11. But we can evaluate this between the bounds, and that will give us the thing. So the integral here is again tricky, but if there's one lesson, it's that surface area integrals actually tend to be nicer than arc length integrals. Come back for a second. Surface area integrals, you have this extra piece out front. And this extra piece out front tends to make life a little easier. Just integrating ds means just integrating the square root. The radius here, which is sometimes your y function and sometimes your x function, tends to give you a little extra piece that you can kind of use for a u sub. Whereas the pure arc length integrals, just the integral of ds, tend to require trig sub more often. So a little lecture logic hint or something to think about as you're working on the homework. If you're doing a surface area integral especially, look for a u substitution before resorting to trig sub. Definitely the same is true if you're doing an arc length integral. You can try to do u sub, but most of the time it won't work. In this particular case, here's ds, right? We could have actually just integrated ds with u sub as well. Same substitution would work, and we wouldn't even have to fart around with this thing. But oftentimes, surface area integrals are actually a little nicer than arc length integrals. They involve similar looking pieces, but the extra term you get from that radius will sometimes help you with a u sub. All right, I'm gonna leave it here. This is the end of 10.2. 10.3 is next, and we're going to miss a class on Friday due to the holiday, which is a bit of a bummer. Let me see where we're at. We are very, very close to the end of the term. So your last day of class, and thus also your last exam, is scheduled to be on Friday, December 3rd. So we're missing the 26th, and we have Monday and Wednesday next week to talk about polar coordinates. And now we could force that into 2 days. I could show you graphing in polar coordinates on the 29th, calculus in polar coordinates on the 1st. There's really only one calculus operation I'm interested in polar coordinates, and it's areas. But that feels a little bit rushed to me. So what I'd like to do is find some way to supplement this lesson. So probably what I'll do is I'll record a little video for you guys where we will introduce polar coordinates, and then Monday and Wednesday of next week we will work with calculus operations and graphing a little bit more in detail. One possibility, if we do need the day for a lecture, is that instead of doing an in-class exam for the last exam here, I might give you a take-home test, but it looks like it's going to fit, and take-home tests are rife with cheating and problems that I don't want to deal with anyway. So a small possibility that instead of having the exam in class on Friday, we will do a take-home test, but I'm going to try to avoid that. So do watch. I'll post an announcement with a video lecture to supplement the day we're losing on the 26th, where I will introduce polar coordinates. This is something that you're supposed to have seen in trigonometry, but I know that not everybody learns this shit in trigonometry. So think of the lecture from the 26th as kind of a review, how to graph in polar coordinates. And then next week, Monday and Wednesday, we will be working with calculus and polar coordinates. And again, there's really just the one operation. I don't care about first derivative stuff or tangent line stuff in the setting of polar coordinates. I really just care about areas. So we're on track to wrap up here in really nice form. Please do work on the current homework set. Take a quick peek at that. Remind you what's there, remind me if I need to add some surface area problems. I don't think I put any surface area stuff in there because we hadn't talked about it. So probably I will slap a few extra problems in there for you to work on. Just 1 or 2 surface area problems. So I didn't label it as a part 1. Maybe it is. I need to put surface area in here. Area enclosed by this, no. So we need to add, oh no, surface area generated by, yep. Okay, yeah, no, we're good. All right, I won't be adding anything to this. This is good. Do watch for that extra video lecture that'll show up on the 26th, or maybe sooner if I manage to get it done sooner. And that's it from me, guys. All right, have a healthy, happy holiday. Be careful, be safe. Make sure to work on some mathematics. When we come back next week, we're going to start talking about polar coordinates. Bye.